Okay, good morning. So we are on our way to understand what people say when they say they corrected for they corrected for multiple testing, they used family voice error rate correction, all these things. Often actually in papers, if you read them, it's a little bit unclear what they mean, because often they don't really know what they did because they used the toolbox, and then it's a little bit hard to write up what you actually did if you didn't really understand it. So we're trying to do our best to understand what's going on. So we still have to complete our multiple testing section that we started last time, and we definitely need to introduce the family voice error rate in multiple testing, and we need to introduce maximum based FWR ER control, because this is the basic starting point for the work in random field theory that was applied to neuroimaging in the early 90s, and until this day is kind of the standard for multiple testing control in neuroimaging. So we first have to finish that, and once we finish that, so I hope to finish that in the first hour, then we can start talking about the basics of random field theory. So, hello, can you close the door? Thank you. So first, to get started, let's briefly remind us of the multiple testing scenario. So we discussed last time that in the multiple testing scenario, like in the single testing scenario, we have a parametric statistical model over data Y. The data Y, you can now think about the time courses of all voxels across the brain. So it's a, if you want, multidimensional data set. And then what we introduced is the multiple testing hypothesis scenario, where in contrast to the single test hypothesis scenario, we have multiple hypotheses. And as we discussed, a hypothesis corresponds to partitioning parameter space into an alternative and a null hypothesis, and this is done here. So the entire parameter space is partitioned like this, where these are mutually exclusive, null hypothesis and alternative hypothesis, and this is done m times. And we discussed last time how, for example, assuming that the expected value at a given voxel is 0, and doing this over all voxels corresponds to specifying m null and the corresponding alternative hypothesis. And we also introduced an index set for the hypotheses. So if you want, these are just the voxel numbers that go from 1 to m. So then we introduced the notions of a complete null hypothesis, which corresponds to the idea that the true but unknown parameter is an element of this complete null hypothesis, which we discussed corresponds to the intersection of all null hypotheses, and we introduced the complete alternative hypothesis, which corresponds to the case that the parameter is an element of this big theta 1, which is the intersection of all alternative hypotheses. And then, so this would correspond to the idea that the expectation for or the parameter, the beta parameter corresponding to a specific condition in the GLM scenario is 0 for all voxels or is non-zero for all voxels. So either no activation anywhere in the brain or activation everywhere in the brain. And then we also introduced the partial alternative hypothesis scenario. That's how we call it. Just looking for this. The partial alternative hypothesis, where the idea is that theta is an element of the intersection of some of the alternative hypotheses. So theta 1i, where this I1 is a subset of I and contains m elements. So these are the m voxels for which the alternative hypothesis holds. And then necessarily a partial alternative hypothesis scenario means that the null hypothesis holds in the remaining ones. So you could also call this whole thing the partial null hypothesis scenario. But I found it a little bit easier when writing this power paper to frame things in terms of the alternative hypothesis, because it's more natural from the random field theory perspective, where this set I0 is just the complementary set to the set I1, so it's the index set minus this indices that are in I1. And we assume that there are M0 null hypotheses, and then of course the entire number of hypotheses is M0 plus M1. Yeah, so that's what we introduce in terms of the multiple testing or multiple hypothesis scenario. And then we introduce the notion of a multiple test, which just comes down to the concatenation of many single tests. So we assume that we have these tests phi I that take the data and map it onto 0, 1. Oops, that doesn't make much sense. And each of them we actually assume to be of this standard form, so that it's based on a test statistic. So phi I of y is the indicator function and comes out 1 if the test statistic of the ith test is larger than some critical value. So essentially this just means that every single test is of the form that you're familiar with from the one sample t-test, and these gamma I are these test statistics. So again, from the perspective of fMRI, if you have a GLM at each voxel, then of course, as we discussed in last year, you can form a t-statistic based on a certain contrast vector. So if you use the same contrast weight vector for each voxel GLM, then you have the same test statistic at each voxel, you have a t-statistic, and so you have a map of t-values. Yeah. So as you already seen in SPM. Now these are the components of the multiple test, and then the entire multiple test is of this big file, which takes the entire data set. Actually, each individual test also takes the entire data set, but of course, if it has the time series from all voxels, then the ith test in the case of fMRI only looks at the data subset from the ith voxel. However, the complete or the multiple test then looks at all voxels and corresponds to, this is still the, is it a typo? No, it's not really a typo. No, there are M tests, so it there are M hypotheses, so there are M zeros and ones, and they correspond to the concatenation of all the individual tests. And last time we also looked at an example for that, how that would look, for example, for 3 boxes. So you should imagine this multiple test just as a vector of ones and zeros that indicates for each voxel whether the alternative hypothesis is accepted or the null hypothesis is accepted, or vice versa rejected. So I think this is as far as we got last time, and then I think we said that now things are a little bit more complex than in the single test scenario, because in the single test scenario the null hypothesis is true or the alternative hypothesis is true, and the test comes out 1 or 0. So reject the null hypothesis or reject the alternative hypothesis. And in the multiple testing scenario, the complication is that the null hypothesis may hold at all, for all tests, so at all voxels, or only at a subset. And if it only holds at a subset, there are many possibilities at which subsets it may hold. And so that's the true state of the world. And on the other hand, also the test can come out 0 for all tests, 1 for all tests, or anything in between. So it's not that immediately clear how to define type 1 and type 2 errors, or I mean there are more possibilities for type 1 and type 2 errors than in the case of the single test scenario. And this is what I want to do then next. So introduce a number of test error probabilities or test error rates. It's the same thing. And among them, there's the family-wise error rate. So they are also called rates. So far to what we did over the last 2 sessions. Any questions regarding this testing setup?
Quick question regarding terminology. When you say one sample simple t-test or t-value, are you referring to a t-test where we are comparing the p, or we want to know if the beta value is equal to 0 or not?
Yeah. But of course the beta, it depends on the contrast weight vector. So if you have a contrast weight vector, if you have 3 beta values and you have a contrast weight vector like this, then the question is beta 1 equal to 0? If you have a weight vector that looks like this, the hypothesis is the difference between beta 1 and so is beta 1 minus beta 2, is this equal to 0? All of these are one sample t-tests, so it doesn't need to be that a specific beta parameter is equal to 0. It can also be these linear combinations of beta parameters, but usually the first example that I give corresponds to the idea that one of the betas is equal to 0. Yeah. But the important thing is that you collapse the beta parameter vector to a single number, and test some linear combination of beta parameters and have one hypothesis with regards to this linear combination. Any other questions? Good. So the best way to, the most straightforward way to understand what's going on in the multiple test scenario is actually, again, to do that with a table that is somewhat reminiscent of the table that you're familiar with from the single test scenario, where you have null hypothesis true, null hypothesis false, test comes out positive, test comes out 0. But now doing this for multiple tests. And this then looks like this. And what these things mean, we'll discuss in a second. So there's some mathematical notation here all the time, which is helpful to express things concisely, but you should always be clear what this means. So this these expressions just mean ith null hypothesis holds. Yeah, so this essentially corresponds to the idea that the null hypothesis holds at voxel I, and of course it can hold at all of them, or at none of them, or at a given number or a given subset of them. And this is of course ith alternative holds. And we already discussed that we call the total number of those, so the number of true null hypothesis, we call this M0, which is the cardinality of this null hypothesis set, and we call the total number of alternative hypotheses that holds, we call that M1, which was the cardinality of this index set I1. And now we can look at our single tests, and of course they can come out 0 and come out 1. Oops, that's too far. And then we can essentially count how much of each we have. So these numbers that now go into these tables, these are the numbers of cases that these things hold. So this this M00 is the number of tests that come out 0 where the null hypothesis holds. And this is the number of tests that come out 1 where the null hypothesis holds. This is the number of tests that come out 0 where the alternative hypothesis holds. And this is the number of tests that come out 1 where the alternative hypothesis holds. And the important thing to realize about this table is that M0 and M1 are true but unknown. Yeah, so that's like the alternative or the null hypothesis holds in a test scenario, which is the true but unknown state of the world. In this case, it's the partitioning of all the hypotheses into true null hypothesis and true alternative hypothesis. So they are true but unknown, so they are not observed. The other thing that is not observed are these values M, I, J for I 01 and J 01. So these are unobservable random variables. So they are random variables, of course, because they are test outcomes, and we discussed that the outcome of a test is always a random variable because it depends on the data, which is a random variable. And the reason that these four numbers M00, M01, M10, and M11 are unobservable random variables is, of course, that we don't know where the null hypothesis holds, so that's just the true but unknown state, and hence what we actually observe is only the total number of accepted null hypotheses, which is this, and the total number of rejected null hypotheses. So again, this corresponds to the case, so think again of phi being a vector of ones and zeros, and this vector just tells you the null hypothesis was accepted at the first location, it was rejected at the second location, it was accepted at the third location, and so on. So here the total the total number of rejected alternative hypothesis accepted null hypothesis would be 4. So M0 plus M1 equals 4 in this case, and M01 plus M11 equals 2. But that's the test observation, and it doesn't correspond to the true but unknown state. Yeah? So it could be that actually this is a mistake, so that at the first location, although the null hypothesis has been rejected, the null hypothesis actually hold, because there are test error probabilities, and it's a random variable, so it can go wrong. It can be that this, for example, is correct, that this is correct, but that this, for example, is a, this would be a type 1 error, of course, at this location if it's false, and this would be a type 2 error at this location if it's false. Let's assume that this is correct and this is another type 2 error. Yeah. So this is the scenario. So in the script you see that again, that's also written in the both forms. So M00 is the number of tests for which the null hypothesis holds, and the tests accepts the null hypothesis, and so on. So again, these are unobservable random variables, but the sums M00 plus M10, that's an observable random variable, as we've just looked at it. And M01 plus M11 is also an observable random variable. So that's the scenario in terms of what can happen. And based on this, one can now define different test error probabilities. Yeah, questions about this at this point? No? So based on this, we can now, now we have to go back to that, but we can now define different error rates, and we will only be interested in the family-wise error rate, but you sometimes see different error probability, test error probabilities being controlled, so it doesn't hurt to be aware that there are more than the family-wise error rate. So the family-wise error rate is defined as the probability, and we do it informally first, the probability for M01, which is theta in theta I 0 and phi I y equals 1. The probability for M0 for the probability for M01 to be larger than 1. Than 0. To be larger or... This is wrong here. It needs to be M0 larger or equal to 1. That's a typo in the script. Because it needs to be 1 or more and not 0 or more. To be larger or equal which is how it is in the remainder, and of course it doesn't make sense. So M01 larger or equal to 1. So in probabilistic terms, the probability of the event M01 larger or equal to 1. Yeah? And not to 0, because that would include the idea that M01 is 0, and that's not an error. That would be correct. So we will go deeper into family-wise error rate later on, so don't worry too much about it now. Just accept that this is the definition of the family-wise error rate. We can define other error rates. And in the script, I discussed the per family error rate, which is the expectation of M01, which is something different, of course, than the probability of M01 being larger or equal to 1. So per family. That's the expectation of M01. The per comparison, which means per test, per comparison error rate, which is the expected value of M01, M01, why do I say so? M01 divided by the total number of hypotheses, M. And one thing that you likely will come across, the false discovery rate, which is often easier significant than the family-wise error rate. This is why it's often reported, because to get significant when the family-wise error rate isn't significant. This is the number of false positives divided by the total number of rejections. So that's number of false positives that's total number of rejections. So here the question is total number of rejections. Of all the alternative hypotheses that I accept, so all of the null hypotheses that I reject, how many of them are false positives? And I want to minimize that rate. So if 5% of my rejections are false positives, I'm okay with it, which is something different than to say that I maximally have a 5% probability to have one or more false rejections, false positives, total number of rejections. So what I'm trying to say here is that based on this scenario, you can define different forms of error probabilities, and each of these error probabilities you can then try to control based on your test procedure. Yeah? So you should really understand these things just as definitions, and if you then construct a test, then with your test you want to control, for example, the false discovery rate, or you want to control the family-wise error rate, and then you design your test accordingly. So the important thing is that you appreciate that there are different error rates in the multiple testing scenario, and a specific test usually controls one of these error rates. There are more than the ones that I discuss here. What this also implies, if you remember type 1 and type 2 error rates in the single test scenario, that if you talk about the probability for detecting an effect if it's really there, so the complementary probability to a type 2 error, so not detecting an effect if it's really there. If you have multiple test error probabilities, you also have multiple complementary type 2 error probability rates, meaning you have multiple types of power. So if you hear people talking about power in the multiple testing scenario, you should really ask them what they mean by power, because like there are different types of type 1 error rates, there are different types of power in the multiple testing scenario. And if you want to evaluate power or maximize power in a study and so on, you really need to be clear about which type of power you want to maximize. And if you want to know more about it, read our paper on fMRI power. But we will not go here into this. So what we will now focus on is the family-wise error rate. And the reason for this is that this has been the topic of multiple testing control in fMRI since 1991. Since Carl Friston first tried to control the multiple testing, the family-wise error rate using random processes there, and fairly quickly after that, Keith Worsley did something else and better, something similar and better, not something else. So the family-wise error rate, as I've shown you, is in the SPM table. It's very prominent in neuroimaging. It's not necessarily the best error rate or the most sensible error rate or whatever. It's just the error rate that is mostly controlled in fMRI, which has to do with the fact that they started this. So one can argue that the false discovery rate is actually a more interesting error rate to control, and then there are methods to control that. However, the family-wise error rate is something that you always see in fMRI. You always have these P, FVE, P values and so on. So it's just there, it's being used, and we need to understand what's happening. Yeah?
I'm not sure if it's easy to explain, but if you said that the small m0 and small m1 are true but unknown values, how can you actually partition the big M's in, as if we knew which hypothesis was the...
No, yeah, I mean, it's like always in statistics, so there's a true but unknown value, and you try to create a method, for example, estimating a parameter, so coming up with an estimator that, for example, in its expectation is equal to the true but unknown parameter. So in theory and in simulations, you can of course assume that you know M0, but in real life you will not M0. We will not know M0, so these M0s, this M0 and this M1. It's true but unknown, so in real life you don't know it. In theory, you can always assume that you know it. But regardless of whether you know it or not, you can of course say, okay, in principle, if M0 is the number of true null hypotheses, then in principle it's possible that that the test comes out 0 for some of them and comes out 1 for others of them. So these numbers, they just follow from the fact, so that you can partition this into M00 and N01, follow from the fact that the test can, because it's a random variable, for the null hypothesis that really hold, the test can either come out 0 or it can come out 1, like in the single test scenario. Now you also, I mean, you do the same thing. You say the null hypothesis holds and the test can come out 0 or 1. And the thing is, in real life, of course, you never observe these values here, because you don't observe these values. So all of this remains unknown, but these, the important thing is that these are not random variables. And these are random variables because they depend on the test, which is a random variable. What you observe are these random variables. Yeah? So they are random variables that you observe because, as I shown here, in the test, you see the 1s and 0s.
So how we partition these n's depends on our alpha level then?
No. This has nothing to do with alpha or anything. I mean, it has to do, if you then it has. So it depends if you want. So this is just a partitioning without saying something about the numbers. If you do this for a concrete test, and let's say you do it in simulation so that you directly can observe the small m's and all the big m's, then of course if you change the test, the things that you will observe here, so the things that you can observe here then will come out different. So it depends on the test, but I'm not discussing right now how it depends on the test. I'm just saying it's just the theoretical statement that when thinking about the scenario, there are multiple hypotheses. So the null hypothesis can hold there, the test can come out this. That's all that we're doing right now. Yeah.
So this is something we can actually estimate. For example, M01 is actually the test where the null hypothesis holds, but we reject the null hypothesis. This is something we can estimate.
Yeah, but we are not there yet.
Yeah.
So be a little patient. So the next thing is that we are going to discuss how we are going to control the family-wise error rate. And there you will see how the test construction then allows for doing something with these numbers. Yeah. Good. Let's have a break now. And after the break, discuss the maximum statistic-based FWR control, because we need a little bit of time for it. So let's start 5 to 9. So.